classes in that to understand how we are to couple fermions to gravity. Now, before coming to the question of coupling fermions to gravity, I was told that many of you didn't know how to describe fermions as spinors. So what I will do this class is not talk about general relativity at all. This class will be a complete digression. Okay, there will be no general relativity, no metric today. I'll just teach you how to do spinor theory. Okay, I'll just teach you how to describe an electron, a proton, and a neutron, or a neutron as a Dirac spinor. Okay, that's what today's class will be. And next class, so by the end of today's class, what we'll have is an action that will describe for us electrons, protons, neutrons. Okay, that will be the Dirac action. And once we have the Dirac action, we can ask the question, how do you couple it to gravity? Right? Just like when we had the scalar action, when we had del mu phi, we could couple it to gravity by just saying, oh, I just have to take the line, space-time volume element and make it invariant by putting a root minus g. And I have to take all the del mu's to d mu's. Right? That's how we coupled scalars to gravity. Question is, once we have the answer for the Dirac action, how do you couple that to gravity? And we'll find that there are complications there and that we'd have to learn new techniques called the tetrads to do that. Okay, so today, no general relativity. I just want to ask, how do you describe fermions? Today will be not so short digression into spinors. Fermions and spinors in flat space. Okay. So before we get to things that we don't know anything about, let's just review things that we know some things about. What we have learned so far are, all of you have seen scalar fields, and scalar fields under a Lorentz transformation, say the Lorentz transformation is given by lambda, under a Lorentz transformation is transform as phi of lambda inverse x. Right? This makes sense. And a vector field A mu will transform as lambda mu nu, A nu, lambda inverse x. Right? So this is a scalar field. This is a vector field. And we know that the scalar field describes scalar particles. So for example, pions. This probably you didn't know, but I'm telling you that a pion is a scalar particle, and that can be described by a field theory of just a scalar field. Okay, Higgs also, for example. And the vector field, this all of you must know, and that the vector field just describes photons, right? Because the vector field describes the electromagnetic field, and the electromagnetic field at the end of the day describes photons, right? But both these examples have no spin. Okay. Both these are bosons. That is, they have no spin. Okay. So in these two examples, these two fields were just given to you, right? You didn't find these fields. You just considered a scalar field, said it will transform this way, and wrote down an action and found that, oh, well, it describes pions. And then you said, oh, there is a gauge field A mu. It transforms this way under Lorentz transformations, and under gauge transformation, it transforms as A mu plus del mu lambda. And then you said F mu nu is gauge invariant and Lorentz invariant, and hence you get electromagnetism. Right? Similarly, I'm just going to give you the answer for the spinning particle for a fermion, right? But there is a principled way, there is a systematic way to find all of the particles. Find the scalar particles, vector particles, spin half particles, spin 3 half particles by doing representations of the Lorentz group. But this I won't go into, right? Because that's more involved theory and you'd have to sit down and do some work. So I'll just give you an answer for how to describe fermions, right? So how do you describe? What about fermions? Like electrons, protons, etc. So basically what you have to do is to study, given a field F, what is happening here. The lesson I want you to learn from these two is that you have some field F, which under a Lorentz transformation gets a matrix R of lambda, gets a matrix R of lambda, and then F of lambda inverse X. Okay, that's what's happening here. In the scalar case, R of lambda is just identity, just some one, so it's a trivial matrix. In the vector case, R of lambda is just lambda. Okay, and you can imagine that there can be more complicated fields where R of lambda will become more and more complicated functions of the matrix. Okay, and basically the point is that all particles in the universe are represented by fields which transform this way. Okay, so I'll give you the answer for the fermions. I mean, this will be a lot to take in one moment. So take your time and ask questions, because this is not really, this doesn't really belong to a GR course. I'm just giving you a very quick lightning introduction to fermions. So it'll be quick, and I'm just apologizing for it. So the answer is that electrons, protons, etc. are described by four component objects. All Dirac spinors. Okay. Now, just because it's four component, remember that A mu was also four component, right? But A mu was a vector, it's not a spinor. Here also you'll get a four component object. You'll get a column matrix of just four numbers, but it won't transform like this. It won't transform like a vector. It'll transform in a more complicated manner. So I'll give you the transformation. So Dirac spinor, I will use psi for a Dirac spinor. Sorry. I'm sorry. Yeah, have integer spin. I'm so sorry. Yeah. Okay. So electron, protons, and etc. All these fermions that we are familiar with are described by these Dirac spinors, and the Dirac spinors transform in a certain way. So I'm just going to write the answer down. This answer will seem complicated, but I will explain it in a moment. So psi of x has to transform as exponential I over 2 omega mu nu psi of lambda inverse x. Now, omega mu nu is just the infinitesimal. So what I've done here is usually what we do in quantum mechanics. In quantum mechanics, you have a generator of a translation, which is say p mu nu, and then you exponentiate it to get a finite transformation, right? E to the I p mu nu. Similar thing I've done here. Omega mu nu is just the infinitesimal version of infinitesimal Lorentz transformation. So basically lambda mu nu, I'll write as identity where nothing happens, plus this omega mu. This is a finite transformation, right? Because I've already exponentiated. If you want infinitesimal, I can just write this as identity plus half omega mu nu. No, infinitesimal part of Lorentz transformation. I mean, you understand what I mean. Okay. So now notice, so there are lots of indices and lots of things happening here. I will come to all of that in a moment. But before that, this is of the same form as that, or that and that. Okay. So this basically acts like a representation matrix, acts as a Okay. So you have the exact same form where a field goes to some matrix times the same field at lambda inverse x. Now notice that this is a matrix. This is a 4x4 matrix, right? Where is that fact obvious? I will tell you. S mu nu. Now, this is why I said this construction will seem a lot to take in for the first time. But S mu nu is 1/4 gamma mu, where gamma mu and gamma nu are matrices satisfying an algebra called the Clifford algebra, which is just this. Okay. This is the answer. Just like people gave you an answer for a scalar field and a vector field, because these are simple. You can just write it down in one line and you can write down everything else. Here, this is a bit more complicated, but this is the answer. So I'll illustrate the answer for you in a moment. So notice that this has to be a 4x4 matrix. This is a 4-component column vector. This is a 4-component column vector. And this is a 4x4 matrix. And that's a 4x4 matrix because gamma mu are 4x4 matrices. Right? Gamma mu's are 4x4 matrices, so their commutator is a 4x4 matrix. And so you're exponentiating some number times 4x4 matrix. So that should be a 4x4 matrix. Okay. So let's. Yeah. I'll try my best. I mean, I will never use the other convention. Eta mu nu is diag. Okay. Also note that most QFT textbooks, I mean, such a thing is usually done in QFT textbooks, and most QFT textbooks use plus, minus, 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 because of which many things here will change. Many things, as in there'll be minus signs made many places, there'll be a minus sign there. And this is another convention. You can either put or not put a minus sign there, etc. But anyway, we don't need all that confusion. We'll only work with the mostly positive convention. So this is the answer. So just to understand what we're doing, I mean, just to convince ourselves that we're not doing something very crazy, let's compute these matrices and convince ourselves that these matrices do exist and they look nice and so on and so forth. Okay. So gamma mu and gamma nu, I'll give you an answer for it that satisfies this. Okay. So the answer is this: gamma 0, 0, identity, 0, and gamma I is 0, gamma I minus gamma I minus sigma I 0. Okay, sigma I are the polymatrices. Okay. Just as a sanity check, let's do one component of this. Polymatrices. You know the polymatrices, right? What notation? Oh, this. Yeah, it's just 1, 0, 0, 1. This is the identity matrix, 2 by 2 identity matrix. Thanks. So this is the 2 by 2 identity matrix. Okay. So just as a sanity check, let me show you that this can be satisfied with these matrices. So let's take gamma 0 anticommutator. And anticommutator is just 2 gamma 0 squared. So this will just be 2, 0 identity 0, 0 identity 0. So this will be what? 2 identity 0, 0 identity. Right? And that's of this one. Because eta mu nu 0, 0 component is -1. -1 into this minus will give you a plus. Plus 2 times this is an identity matrix. 4 by 4 identity matrix. Okay. So this is exactly that form. This is 2 eta 0, 0 identity matrix 4 by 4. Okay. Similarly, you can check all of the other components and it will work out. I can check one more if you want. Yeah, maybe one more. Gamma 0, gamma I, let's do. So this should be, what do you think the answer for this should be? 0, right? Because eta 0 I 0. So let's do this: 0 identity 0, 0 sigma I minus sigma I 0 plus sorry, minus sigma I 0 0 which is indeed 0. There's only one more line to check actually. You just have to check gamma I, gamma j. Okay, if you want, I can do it, but I think you understand the point, right? So basically, once you have these gamma matrices, you can, so this step is solved, okay? So basically I'm saying once you have these gamma matrices, compute their commutators, okay? And those are the generators of the Lorentz group. So these are the generators. So you have those gamma matrices, someone just gives them to you. I mean, all of this can really be constructed, but I'm just giving you the answer. So I'm just giving you the answer for the gamma matrices. From the gamma matrices, compute their commutator, and that will be a generator. Once you have the generator, you just have to exponentiate it with parameters, right? For example, what do you do when you have a momentum generator? For example, so this is just again a shorter digression into generators. Once you have, say, p mu, which is the momentum, how do you exponentiate it? You just exponentiate it with I a mu p mu. Where a mu can be any 4 vector, right? Right? Depending on what translation you want. If you want a translation along the x direction, a mu should be 0, 1, 0, 0. Right? Similarly, Lorentz transformations, there are many, many more of them. Right? Lorentz transformations, there's a whole omega mu nu of them, where omega mu nu down is antisymmetric matrix. Right? There's like, there you can do rotations, you can do boosts. Right? So basically, once you have the generators, you just have to dot it with the infinitesimal Lorentz transformation, and you get the full transformation, full Lorentz transformation. Okay. Anyway, so this ends our first goal, which is how do you describe fermions? Okay. So what have we learned so far? We have learned how to describe fermions. Okay. This is like 2-3 classes of a quantum field theory course in 10 minutes. But we only really need the answer because next class I want to do GR with this. So this is the answer. So basically what I'm saying, just to recap once again, because this is very new, is that we knew how to describe pions because they were scalar fields, and scalar fields transform this way. Somebody just gave you the answer and then you could write down a Lagrange. And then you said, oh no, and now I want to describe photons, I want to describe light. But that we already know classical theory for. It's just some a mu. So then you wrote down a mu and you saw that Lorentz transformed this way. From here, you could write down an action and that described fermions. Similarly, you have to do some principal work, but I'm giving you the answer that what you have to do in order to describe electrons and protons and so on is to consider a 4-component field psi, which transforms in this way under a Lorentz transformation, which looks like this. Okay, good. Next step. What do you do next step once you give a field? You're given a field. That's not useful. I am telling you, well, that is useful. I'm giving you a field, and that describes a pion. But now I have to tell you what the pion's dynamics is. Right? How does the pion move away in space-time? What does it do? What dance does it do? For that, you have to give me a Lagrangian. Right? For a point particle, you give me a Lagrangian, then I can tell you how the point particle moves, Newton's laws. Right? Similarly, here and there, I have to construct a Lagrangian. So that's the next question I want to try to answer. Let me see if I'm missing something I wanted to say. Yeah, I also wanted to give you, so since you might want to go home and write down these exponential matrices and see that it looks nice and so on. I also wanted to just write down an examples of S mu for you. So for example, S0I is what? Is I over 4 gamma 0 gamma I, right? This I can just compute. So let me just compute. Is just okay. Subtract which two lines? Yeah. Okay, great. What's the answer then? Thanks. So this is minus iota over 2. Minus. Let me just check with what I had. Yeah, that sounds right. And similarly, you can also check that Sij will become half epsilon ijk sigma k 0 0 sigma. This you can check. You notice a very interesting fact. I will not give you more details about this, since I guess Surat is going to teach you fermions soon. Today, great, is that this is not a Hermitian generator. Usually in quantum mechanics, we always have Hermitian generators. We never have non-Hermitian generators. But here you don't have a Hermitian generator. This is really non-Hermitian. Okay. And that becomes an important fact, and then you can learn more about it and so on and so forth. But I just wanted to say that very quickly. Okay. Yes, they correspond to boost. So these are rotations. These are the rotation generators. And these are the boost generators. And that's appropriate because you need 3 boosts. There are 3 boosts. And you need 6 rotations. 3 rotations. And there are 3 rotations because these are antisymmetric. Sorry, 6 Lorentz rotations. Anyway, so that's all I'm going to say about that. Anything more maybe? Yeah, so one more thing I wanted to say is that I will not tell you how spin comes from this and how you can get fermions and antifermions and so on and so forth, but roughly, very, very roughly, you can already see that there should be spin in the game because there are sigmas here, right? And there should be only 2 spins because there is again a sigma. And sigma is just plus half minus half. So roughly, very, very roughly, at a very symbolic level, you can say that you can see that what I've written down, the psi I've written down, really describes spin half particles. Right? And electrons, protons are all spin half particles. And so this describes the spin half particle. Okay, that's very rough. Anyway, so now let's go on to dynamics. How does the field psi evolve? In other words, what is the Lagrangian? Okay. So let's recap a little bit. So just like I did here, I gave you a scalar vector and then I gave you an answer. Similarly here, let's recap scalar vector and then I'll give you an answer. And this time the answer I will explicitly sit down and check the whole thing. Okay. So recap. Recap of scalars and vectors. In the case of a scalar, so scalar, you know that phi of x transforms as phi of lambda inverse x. So then if I write down, so terms permissible in the Lagrangian, so So I will write down in yellow terms permissible in the Lagrange. So if I write down phi squared, okay, and then integrate over all space, this is clearly invariant, right? Because if you do phi squared of x, how does this transform? This transforms as integral d4x phi of lambda inverse x, phi of lambda inverse x. But then you can call y as lambda inverse x. And so this will just be equal to integral d4 y phi of y phi of y, which is the same as what I started with. And why does this measure not change? Because under a Lorentz transformation, measures don't change. Right? d4x, when you do a Lorentz transformation, it remains d4x. Okay? So we found that phi squared is an admissible term in the Lagrange. Similarly, you say, let's consider del mu phi, because I want some dynamics. I want some space-time variation of the phi. If I just wrote down phi squared, everything will just be same. Okay? In space-time, I want things to change. I want some del t's, del x's, etc. So del mu phi transforms as what? Del mu phi transforms like this. Okay. So then clearly, if you do del mu phi down, del mu phi up, these matrices will go away. Okay, because the property of the Lorentz transformations just be lambda inverse, and they will go away. And therefore, del mu phi is also admissible. And you can run this argument for del mu phi as well. Okay. Therefore, you construct the simplest free, I mean, you can of course do phi to the 4, phi to the n, you can just keep going on. The simplest, so free scalar action, you can write as minus half. This minus half is just some number outside. Right? Doesn't matter at this point, but you'd have to put the minus half if you're coupling it to other things. d4x del mu phi plus m squared phi squared. Okay. And so you constructed scalar theory. So that gives you scalar theory. Now let's come to vectors. In the case of, let's say Maxwell. In the case of this, you have a mu, which transforms like this del mu. Okay. But you also say, I want a gauge invariant theory. Okay. Let's say I want a gauge invariant theory. On top of Lorentz invariance, I want a mu going to a mu plus del mu lambda invariance as well. Okay. A gauge invariance forces you to consider something that does not have any lambdas under this gauge invariance. So this, so gauge invariance forces us to consider this is gauge transformation, this is Lorentz transformation. Consider f mu nu defined as del mu a nu minus del mu a mu, which under a gauge transformation just remains the same. So I have trivialized the gauge transformation. Once, if I write the action in terms of just f's, gauge transformation is obvious because f doesn't change under gauge transformation. And now how do you make a Lorentz invariant thing? Just like I did it here. You just contract indices, so all the lambdas will just do lambda inverses and then just go away. And you run this argument that I did here. And so you get S Maxwell. It should be written in terms of just F, and all the F mu nu's should be contracted. Okay. Now I want to do this for fermions. You want to do the same procedure. For psi. Yeah. So far things make sense. So already you can see that for fermions, you can't do it in one column like I did it here, right? Because fermions has this exponential S mu nu has gamma mu nu. So you'd have to do some work, but I'll do that work now. Okay. Are you guys okay with me using that board? Don't really want to erase this. So. Oh, recording. Okay, fine. I'll bring this down. So for simplicity, let me consider an infinitesimal transformation instead of a finite transformation. A finite transformation, you can just build it up by putting infinitely many infinitesimal transformations together. So let's consider an infinitesimal Lorentz transformation. Under which psi of x will go to identity. This is a 4x4 identity matrix, remember? There are many different identity matrices going on here, so I'm just cautioning you. Plus I over 2 omega mu nu, which is treated as small now, S mu nu plus dot psi of lambda inverse x. I don't want to write this explicitly in terms of omega mu's and so on first order. I'm just writing lambda inverse x. Okay. When need comes, I will write it properly. Okay. But I don't want to carry along omega mu nu's inside the argument. So I'll just write it as lambda inverse x. So this is the infinitesimal transformation. So let's try constructing a scalar. So there I gave you a transformation and I constructed a scalar which is phi squared, integral d for phi squared. So here, what do you think of a scalar will be? Guess, any guesses? Like for example, this was for a real scalar field. If you had a complex scalar field, what did you do? You would do phi star phi. Right? So here, size, if you want to think of them as like a 4x4, 4-member column matrix, and all of the entries are complex. What is the naivest scalar you'll write down? Psi dagger psi? Let's check psi dagger psi. So, but then you want it to be real, so psi dagger psi. So, what about psi dagger psi? So now let's just see how psi dagger transforms. Psi dagger of x, by just taking a dagger of this transformation, will transform as psi dagger lambda inverse x. Identity will not, nothing happen to the identity will be identity. Minus I, because this I will get omega mu nu. And S mu nu is neither Hermitian nor anti-Hermitian. Because some components of it are Hermitian, some components of it are non-Hermitian. As I noted there, because S0I are boost generators which are non-Hermitian, Sij are Hermitian. So I'd have to just write dagger here. Then you have nothing. Okay. Now if I just multiply psi dagger and psi, at the linear order, these two won't cancel. Because S mu nu dagger is not the same as S mu nu. So psi dagger psi doesn't work. Okay. So at this moment, you have to have a stroke of genius and say, why not consider? Actually, it's not too much of a genius either, because you want to consider some matrix, some version of psi dagger, such that it'll have a matrix here, which will go through this and make this an S mu nu with a minus sign here. If this were an S mu nu, recall that if this were an S mu nu, so let me say this once again. Let's say, so psi dagger transforms this way. This is the correct transformation. But let's say This dagger wasn't here. So then these two, if I do psi dagger psi, it'll just go away. These two terms will just go away. It'll just be, so let me do that. So psi dagger psi transforms as what? Psi dagger psi transforms as this multiplied by that. So there will be a psi dagger lambda inverse x identity plus half omega mu nu s mu nu minus half omega mu nu s mu nu dagger plus dot dot psi lambda inverse x. Is that okay? So if this were an S mu nu, psi dagger psi would have been nice, and I could have written it in the Lagrangian density. So I should do something in order to make this an S mu nu. Okay, I should multiply by a matrix in order to make it an S mu nu. So if you play around like for 2-3 minutes, you'll actually get it. But let me give you the answer. Why not consider psi bar defined as psi dagger gamma 0? Okay. Then psi bar will transform as what? Psi bar of x will transform into psi dagger times this okay. So one thing I forgot to say is that I'm using capital omega for the infinitesimal part of the Lorentz transformation. Most textbooks will use little omega, but I'm at a point where I can't use little omega because next class I have to use little omega for something else. Okay. And that notation I can't really change all that much. I don't want to. So I'll use capital omega. So now the point is that gamma 0. So let me write this out explicitly. So this is psi dagger lambda inverse x identity 4 by 4 minus I over 2. Let's do omega 0 I s0 I, but there'll also be omega I0 s I0, and both of these are antisymmetric. Okay, omega has to be antisymmetric because it's Lorentz transformation. S has to be antisymmetric because I defined it as a commutator. I erased it. So there'll be a 2 from there. And S0 I dagger is minus S0 I. So S0 I. This 2 I'll get rid of that. Okay. And then you have minus I over 2 to omega ij. Sij dagger is just anyway Sij. Okay. Now let's see how gamma 0 commutes or anti-commutes with S0I and Sij. Okay. So let's first compute the commutator of gamma 0 and Sij. Or let me do that after saying the answer. What happens is that gamma 0 commutes with Sij and anti-commutes with S0I. Okay, I'll prove this statement in a minute. I'll prove it in a minute. But accepting this statement, what does this become? This gamma 0 goes through. Here it won't give you a minus sign. Here it will give you a minus sign. And gamma 0 psi bar, psi dagger is psi bar. So this gives you psi bar, lambda inverse x, identity 4 by 4, minus I over 2 to gamma 0 I S0 I, minus I over 2 to omega ij Sij. You see what has happened? Gamma 0 commutes with Sij, so it just goes through Sij without a minus sign. But it anti-commutes with S0I and it will give a minus sign. And that is exactly what we wanted. So if you had played around here, you would have found a matrix such that this happens, and that matrix would have to be gamma 0 or some multiple of gamma 0. So this is exactly psi bar lambda inverse x, identity 4 by 4 minus I over 2 omega mu nu s mu nu. And this is what we wanted. We wanted something that will transform in this way. Therefore, psi bar psi is a scalar, or integral d4x psi bar psi. Yeah, well, okay, fine, is a scalar. Okay. So an admissible term in the Lagrangian is psi bar psi. I put some coefficient m psi bar psi. We've already found one answer. So we have found the equivalent of phi squared. That's psi bar psi. Okay. Now let me prove this statement that I made here, that gamma 0 commutes with Sij and anti-commutes with S0i. I can just do that here. So gamma 0 S0i commutator, anti-commutator is what? Gamma 0 is here, which is 0 identity, identity 0. S0i I computed, so let me put the minus half outside. Sigma I 0, 0 minus sigma I plus sigma I 0, 0 minus sigma I 0 identity, identity 0. Okay, and so this is minus half. Zero minus sigma I 0 plus 0 sigma I. I proved this statement that gamma 0 anti-commutes S0i, that justify that minus sign there. And let me prove also that gamma 0 commutes with Sij. Sij has a half epsilon ijk, so I'll pull that outside. And then you have 0 identity, identity 0, 0 sigma k. Sorry, I think, yeah, sigma k 0, 0 sigma k plus sigma k 0, 0 sigma k, 0 identity, identity 0. Okay, which is half k. Sorry, minus 0 sigma k 0 minus 0 sigma k 0. So I proved both these statements, that gamma 0 commutes with S0i and anti-commutes with S0i, Sij and anti-commutes with S0i. And thus we have found one answer, psi bar psi. But that's at the same level as phi squared. And again, I complain that I want dynamics. So I want something that involves del mu psi. Okay. So let's write down another term that has del mu psi. I'll leave that there. I erase this. So I want some term which has a del mu psi. But obviously the Lagrangian, you should not have indices hanging around. So just to get rid of that index, let me put a gamma mu. I could have done this with another del mu, but I need not have. I want to write down the simplest number of derivatives, smallest number of derivatives, and I can do that with a gamma mu. And just to make this look the same as this, let me put a psi bar. If you don't want to, don't find how this transforms, And then you will see it does not transform as a scalar, and then you'll find that you would have to put a psi bar. But from here, we already learned that if you have some psi, then you have to put a psi bar to make it a scalar. So similarly, you have some psi here, which you're doing some operation on. And since you have contracted indices, it's fine. So you have to put a psi bar. Heuristic. Yeah. 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 Exactly. Exactly. Great. That's awesome. So psi, remember, is a four component column vector. So psi bar psi, since psi bar is psi dagger times gamma 0, it will be a 4-component row vector. And then row vector column vector will give you a number. Same thing should happen here. As he's saying, this will transform as a column vector. You don't want a column vector in Lagrangian, you want a number. So you do it. You could have instead, for example, put a psi dagger here, but then you'll run into the same problem and you'll see that you have to put a psi. So let's check how this transforms. This will take out some time, but let's do it. Because at the end of the day, we'll get something nice. Transforms as psi bar. Psi bar, I already know how it transforms from there. Just identity 4 over 4 by 4 minus I over 2 omega mu nu S mu nu. Gamma mu just remains gamma mu. Del mu, remember, has to transform with the lambda, right? So you have lambda mu nu and then del nu and then psi. So, and psi transforms as that. Okay. The arguments of psi are all lambda inverse x. I won't write it explicitly anymore because I've written it quite a few times. By now, we all know that it has to transform this way. So this lambda mu nu, since it's an infinitesimal transformation, is really just a delta mu nu plus this omega mu. That's how I defined omega mu. Okay. So now we just have to sit down and do some algebra. Not good. Wait. Let me say alpha beta, gamma delta, gamma delta. This algebra will take some it'll take some 5 minutes, 5-6 minutes. And in doing this algebra, we'll require a commutator. Okay. Let me find that commutator. Or I can show you that commutator arises. Let me do that later. So you have a psi bar. I might make a mistake here, so correct me if I'm making a mistake. I want to write everything up to order omega, right? So what is the first term? First term is just this identity hitting this, hitting that. Okay, so I'll just be del mu times an identity. There's an identity 4 by 4 del mu. Psi I will keep outside. Gamma, yes, thanks. Exactly what I meant. Gamma mu del mu. Next, let's do this term. Okay, since I want order omega, this has to hit this and then that. So I'd have to do minus I over 2 omega alpha beta S alpha beta gamma mu del mu nu, which makes this a del mu. And then you get this bit, identity I'll just not write because understood, and then you have psi. Sorry, I'll write it outside. There should be a psi. Okay, what are there are 2 more terms, right? Understand, there are 2 more terms. So we're done with this. Now let's come back to this. Let's do this with this and then that. That's also order omega. So that'll give you what? Psi bar I've already kept. Identity I'll not write. Let me just not write the identity. And what do you get? Gamma mu, indeed, gamma mu. Omega mu nu. Del nu, but I want everything down. So let me pull this up. I just pulled this down and pull that up. That up. That's fine. Del nu, and then psi. Something dot. Okay, fine. Maybe it's right. We'll find out. If it's wrong, we'll come back and do it again. So then final term is where you pick up this omega, which comes from what do you get? You get a gamma mu, delta mu nu, which will make this a del mu. And then you get omega gamma delta s gamma delta, but there is a I over 2. And then you get a psi outside. Okay. Already you can see that we are doing much more work than we did in the case of scalar, right? Because there are all these s and omegas and so on and so forth. Okay. So this is psi bar, gamma mu, del mu. So let me pull that term outside first. So what we want is that these three terms should cancel, right? Because what I want at the end of the day is for this to be a scalar. So this has become what? It's just become psi bar, gamma mu, del mu, psi. That's the first term. And the rest should cancel. Okay. So let me write it in that form. So this has become psi bar, gamma mu, del mu, psi. And what are the other terms? You have plus gamma mu, omega mu nu. Let me write it this way. Omega mu nu, gamma mu, del nu. And you have I over 2, gamma mu, or omega delta, alpha beta, gamma mu, s alpha beta. Psi bar and a psi. Del mu, yeah. You agree? This term is here because I by 2. Let me change these indices as alpha beta. So I by 2, psi bar, omega alpha beta, it's just a number, remember, these are just numbers, these have rapidities and rotation angles. So omega alpha beta comes out. And then you have gamma mu, s alpha beta, and del mu psi. These are all constants, right? But good point. When you do GR, Lorentz transformations have to be defined locally. I can do a Lorentz transformation here, you can do a Lorentz transformation there when you're in a curved spacetime. So this changes. Okay. But we'll see that next time. But for now, everything is in flat space. So del mu won't act on that. Del mu will just go through. It will become a del mu psi. And this term is just the second term from here because gamma mu has to come there and s alpha beta has to come here. So what we want is this commutator. And we have to show that this commutator is a certain thing such that these two terms cancel. So let's do that. Okay, let's find the commutator of gamma mu s alpha beta. Gamma mu s alpha beta commutator is what? It's just I over 4 because s alpha beta has an I over 4. Gamma mu, gamma alpha, gamma beta minus gamma mu, gamma beta, gamma alpha. Right? Because s alpha beta is I by 4 commutator of gamma alpha, gamma beta. And I've just written down the commutator explicitly as gamma alpha, gamma beta minus gamma beta, gamma alpha. Okay. Now you use the formula for ABC commutator. Remember that what we do know are gamma mu, gamma nu anti-commutator. Because gamma mu, gamma nu anti-commutator is minus 2 eta mu nu. Remember that that's how gamma matrices were defined, right? So ABC anti-commutator is just AB C minus something. I mean, you can just write it down, I suppose. So this has a BAC, but I have to get rid of the BAC. So I probably will have BAC. Is this right? So this gives you an ABC plus BAC. So that gets rid of this BAC. And then here you have minus BCA. This works. So let's use this there. So gamma mu, gamma alpha, gamma beta. First you have to do gamma mu, gamma alpha anticommutator, which gives a minus 2 eta mu alpha. Fine. Remember that, I mean, I see too many blinking faces, so gamma mu, gamma nu, remember is just that. Okay, so I'm just using that here for the first term, and then C is gamma beta. This term is minus gamma alpha, and then you have a 2 eta mu beta. Now we come to this one. Now this is just beta alpha reversed. So I'll just take this, put a minus sign, beta alpha reverse. That term is the same as that term. This term is the same as that term. So I'll erase the second line, put a 4 there, but the 4 will cancel this 4. So you get this. Okay. So let me do this contraction now. So therefore, I over 2, omega alpha beta times this commutator is what? I over 2. This height that I gives a minus sign. So that's a minus half omega alpha beta. This minus sign I will pull inside and write gamma alpha eta mu beta. Sorry, gamma beta eta mu alpha minus gamma alpha eta mu beta. Is this okay? So here what happens? So you get half. There's an I over 2. Here. No. See, each of these terms, there'll be a 2 and a 2, and then there'll be another 2 and a 2. These add, get a 4. So what is this? So this will be, can you do this? Omega mu beta, gamma beta minus alpha omega. You're very unhelpful, all of you people. Really? If I'm fast, you should slow me down. Wait. Work. It'll work. Patience. Okay. So now this has to cancel with this term. As he's saying, not yet. Let's put everything together. So let me just consider this. Otherwise, there's too much to write down and there's no board space. So let me consider this. Okay. And let me write it here. Good that I left the space. So I have psi bar, omega mu, gamma mu, del mu, psi. And then I have plus psi bar. This thing I evaluated there, right? So that gave us something's odd. Yeah, it's fine. Half omega mu alpha gamma alpha minus omega alpha mu gamma alpha. So yes, just a minute. Just a minute. Yeah, what do you want? Okay. So let me bring this down, bring that up, because I know properties of omega when both things are down. But omega is antisymmetric. So this really is psi bar omega mu nu gamma mu del mu psi plus this is antisymmetric, so this will become 2 times omega mu alpha or minus 2 times omega alpha mu. I'll choose the minus sign. So it becomes minus, the 2 cancels and you'll get omega alpha mu gamma alpha del mu psi. And obviously those 2 cancel. I'm going fast, you should slow me down. Saying that once again. Okay, so what have we found? Therefore, psi bar gamma mu del mu psi is a scalar. Okay, so now we can put this into the Lagrangian. But one last check before we put this into the Lagrangian is whether this should be real. Because at the end of the day, when you write down a Lagrangian action, it should be real. So let's check if this is real. Turns out this is complex. It's purely imaginary. Okay. So to make it real, I just have to put an I. So I'll put an I and check that it is real. I mean, I can understand that there is so many things thrown at you in some very little time, but it's the best I can do. Well, I could have just written down the final answer Dirac action for you and said we can just do GR with it now, but I wanted to spend one class in setting up all this. So let's consider I psi bar gamma mu del mu psi, and I have to show that the star is the same as the same. Okay? That this is real. So let's do it. So how do you act a star on this? This will go front and put a dagger on it, because star is the same as dagger when you have a real number. I mean, when you have a number. So del mu psi dagger, and the I will become a minus I. And then you'll have gamma mu dagger, and then you'll have psi bar dagger. I've just done A, B, C. Star is C dagger, B dagger, B dagger. Okay, so minus I del mu psi dagger. Del mu, remember, is just some real derivative, so dagger will just act on the psi. Gamma mu dagger depends, right? I think, oh no, I haven't erased it. Here gamma 0 dagger is just gamma 0. Gamma I dagger is minus gamma I, right? So I'll just write it as gamma mu dagger for now. And then psi bar is psi dagger gamma 0 dagger equal to minus I del mu psi dagger gamma mu dagger gamma 0 dagger, but gamma 0 dagger I just told you is gamma 0 psi, because psi dagger dagger. Now let's do this one by one. Let's do minus I del 0 psi dagger gamma 0 dagger, which is gamma 0. So you have gamma 0 psi plus del I psi dagger. Gamma I dagger is minus gamma I. So you get minus gamma I gamma 0. Is okay? Cool. Great. So now this gamma 0 I can pull inside and make this a psi bar. So it becomes minus I del 0 psi bar gamma 0 psi. Gamma 0 anti-commute by that. Gamma 0 anti-commute is 0, so gamma 0 anti-commute. So if I pull the gamma 0 here, that'll give an additional minus sign. Let's get rid of this minus sign. So it becomes plus del I. Once the side gamma 0 comes here, this becomes a psi bar gamma I psi. Okay. Any step is not clear, you should ask. So this becomes minus I del mu psi bar gamma mu psi. Which is still not the same as that. What do you think we should do now? Huh? We were supposed to show that this star is the same as this. It's not that. But remember that this goes into a Lagrangian. So total derivative terms become boundary terms. So let me do an integration by parts. It's easy. That can be written as minus I. So let me say del mu of minus I del mu, sorry, psi bar gamma mu psi plus I psi bar gamma mu del mu psi. Cool. And that you will choose boundary conditions such that psi bar and psi decay at infinity. So del mu will not contribute in the Lagrangian. So we can just ignore this term safely. And we have shown what we wanted to show. So ignoring the total derivative I psi bar. Let me write this as psi bar I gamma mu del mu psi star psi bar I gamma mu del mu. But I would have to end up showing that. So I mean, you know that. So yeah, sure. Indeed. But I mean, since this is the first class, some of us are seeing gamma matrices. This is simplest way to do it. Okay, so this is, so we have found, so admissible terms in the Lagrangian. So we can put, let me just write down the answer. Okay, and let me just write down the action. Therefore, we may write an action. It's Dirac, let's call it, equal to integral d4x. What all terms are permitted? This term is permitted and psi bar psi is permitted. So let's write this term first. Psi bar I gamma mu del mu. And then psi bar psi is also permitted. Let me just put that here. And this is the Dirac action. And this is what I wanted to get to. So this is the action that describes electrons, protons, and so on with a mass m. Now, the interpretation that m is a mass, so on and so forth, you will see from your QFT course, but all I wanted was an action that is invariant under that Lorentz transformation I wrote down for psi. And this is that action. Okay, awesome. I am slightly ahead of time, so I can start some new things as well, which I want to do next time, which is coupling this to gravity. I will come to that. But before going there, let me just pause for 2 minutes and just say if you have any questions, now was the right time to ask, because we're not going to discuss spinor theory anymore. I'm going to couple it to gravity. Okay. So one important thing to notice is that this whole thing, from the beginning, it was a direct digression into fermions and spinors in flat space. So there are many flat space things that went in here. For example, Atharva at some point asked, why did the del mu go through that? Because things are in flat space. Eta mu's are used there because these are in flat space. So you might think, oh well, to make it curved space, why don't in the Clifford algebra I put G mu, I make it flat, and make the gamma matrices depend on space time. Probably something you can try. You'll soon find out that it won't work. Okay, but let me explain why won't it work by considering all this once again. So from now on, I'll just take this answer and I'll just work with this answer. I will not say, oh, psi is powered by four component spinor, psi transforms in a certain way, it has to be Lorentz transformation invariant, so on and so forth. Just like when you write down Maxwell theory, F mu, you don't say, oh, there is an A mu, and then you can construct an F mu, and the Lorentz transformation, gauge transformation. All that stuff you don't say, because once you have F mu, that is the answer. F mu. Similarly, I will treat this as the answer, and we want to start studying this Dirac action. Great. So let me probably go to that board and do the rest. So wait. This was end of digression. Okay, now I don't need all these matrices anymore, because I will assume from now on that they're all masters in doing this theory. So I'm going to erase all of this. And I think I need 2 columns to do this. So let's come back to general relativity. How do you couple fields to the metric? Coupling fields to the metric. Let's do a quick revision of that. I'm not going to start anything very new today. I'm just going to give you an introduction to the next class, and the next class we do all the new things. So how do you couple fields to the metric? So if you have a scalar field, we found that scalar, actually free scalar coupled to the metric. I mean, it's a ghastly notation, but what can you do? In free space. So let me do this. Flat space, flat, curved. Flat space time, curved space time. Flat space time, we know how to write down free scalar. That was just minus half integral e for x del mu phi plus m squared phi squared. Okay. And we learned how to take it to curved space. That was very easy. We said that we should preserve general coordinate transformation invariance. So we should not have d for x, we should really have root minus g d for x. If you remember, I showed you in some tutorial that d for x root minus g transforms in such a way that it becomes d for x root minus g. So this transforms to free scalar in curved space time with a metric g minus half d for x square root minus g. And all the covariant or the partial derivatives become covariant derivatives. In the case of a scalar, partial derivative and covariant derivative are the same, but nonetheless, for consistency, let me just, for uniformity, let me just write d mu phi d mu phi. Square. That's good. So given a scalar theory, we know how to make it couple to gravity. We know how to make it talk to gravity. So this, for example, to describe a pion field in a curved spacetime. And then we learned how to couple Maxwell to gravity. Maxwell in free space, I mean in flat space time, was just T4x F mu nu, F mu nu. Again, you run the same machine and you write Maxwell in a curved spacetime, which is minus 1 minus 4 d4x square root minus g. And then you raise and lower with the metric. So F mu nu, F rho sigma, mu rho, mu sigma. Right? And F mu nu was just, F mu nu still retains its form. It's just del mu a nu minus del mu a mu. You might ask, what if you put covariant derivatives? That's the same thing because the antisymmetric term cancels. Okay, so we know how to couple pion fields to gravity. We know how to couple photons to gravity. And at this point, you might think, I can put any field and couple it to gravity by the same prescription because all I really need to do is to take all covariant derivatives, all partial derivatives to covariant derivatives, and any Lagrangian I know has partial derivatives. I just have to take del mu to d mu, and I just have to take d4x to d4x root minus g. Okay, and this is where the surprise comes. So if you had already known spinors and so on, all of this stuff that I said in the last 1 hour, which might have been overwhelming, if you had known all that, this is where the real surprise comes. This is where the GR part of it starts. Let's do S Dirac. Okay, what was S Dirac? S Dirac was just d4x psi bar I gamma mu del mu minus m psi. Okay, what do you suspect will happen? I'll put a question mark there because we don't know this yet. And I will put a question mark in the action as well. What do you think will happen? d4x by the same argument, I should probably make it d4x root minus g. So let me make it d4x root minus g. What about the rest? I put a psi bar. Maybe I should make this a covariant derivative. So let me write I gamma mu d mu minus m psi. You throw your hands up and say, done. Okay, but this doesn't work. Yeah, that's another interesting property of the Dirac action. So if you vary this action, you'll get the Dirac equation, and the Dirac equation is just this. This is the Dirac equation, and the Dirac equation is a first order equation. It's not a second. Klein-Gordon is second order. Okay. If you put, actually Klein-Gordon will be a consequence of this. So the psi will actually obey a Klein-Gordon, okay? But it obeys a more stricter equation, which is this Dirac equation. Okay, and if you have done some in basic quantum mechanics, if you have seen the Schrodinger equation, okay, Dirac's insight was to write down something that treats time and space equally. Schrodinger equation treats time as a first order derivative, space as a second order derivative. So what Dirac wanted to do was to write down an equation which has first derivative in both space and time. So what he effectively wanted to do was to fractionate or like take a square root of that Hamiltonian, right? And that square root is exactly this, because if you take this and put one more of it, you will get Klein-Gordon. Okay. But all of these are surprises that you should see in the quantum field theory course, which when you see it for the first time, you wonder, and it's very nice. But I'm again apologetic about the fact that I can't go into all of that now. But let's focus on other surprises, because GR also gives you surprises. So let's say this is the answer, okay? Because I've done the same thing as what I did in free scalar and Maxwell. So maybe this is the answer. But then psi, notice, does not have a Lorentz index. I mean, it does not have a space-time index. There is some column matrix, but it does not have a space-time index. So how should I treat this del mu? Should I treat it as a partial del mu? Let's say then partial del mu. Okay. But now gamma mu's are just constant matrices. They're just some matrices defined by the Clifford algebra. Del mu, though, of course, transforms, right? Del mu under a coordinate transformation, general coordinate transformation, that's what I'll call a GCT, transforms as what? Del x over del x prime mu, mu, del mu. So gamma mu del mu, since gamma is just a constant, gamma mu del mu will just transform with this matrix. And everything else, nothing else transforms here. So then the action is not general coordinate transformation invariant. So it's not gravitational. Coming to that. I'm saying naively, we see at the moment I've said that psi, let's treat it as a scalar because it doesn't seem to have an index. Okay. So if you naively think that psi was a scalar, actually his point is, I'll come to it. So if you naively treat psi as a scalar, things don't work out. This is not general coordinate transformation invariant. Okay. So at this point is when in a GR class you say, oh well, psi is not a scalar, it's a spinor. But that surprise is ruined for you because I've been doing spinors for the past hour. So psi you should not really treat as a scalar, it's a spinor. Okay. And psi should be defined with respect to all these Lorentz transformations. Okay. And the spinor actually has to be defined in a local rest frame. So I come to my frame, things are flat around me. For me, I can do this analysis. Okay. But for you who's sitting elsewhere, who's related, or for you who's in a different coordinate system, okay, I have to take this flat space here and translate all of these results for you. To do that, I have to stitch flat spaces together. Flat space for me and your flat space, I have to stitch them together. So I want to have a covariant derivative to go from my flat space to your flat space. So I have to do all that algebra. First of all, I have to tell you how to treat flat spaces, how to treat locally flat spaces. So that formalism is the Weilbein co-Weilbein formalism or the tetrad formalism. And that's what I will do next time. Since I have more time, I'll say more things. But the conclusion from this is that we need to learn more GR. To write down a general coordinate transformation invariant action, we need to do more work.
Started from this local inertial coordinate system, and then we actually saw that if we define everything as a rank 0 to tensor, then everything works out fine and we can get it. Why can't we do something similar for?
You have to do the same thing.
Basically, it was have to define.
Yeah. But how do I say this? There are two things going on. There are frames and there are coordinates. You can be in one frame and you can choose many different coordinates, and this should be clear to you from an assignment problem, right? If you remember this assignment problem where you did this uniformly accelerated observer, the uniformly accelerated observer itself you can write in spherical coordinates or polar coordinates or cylindrical coordinates or Cartesian coordinates. And spherical was the simplest for you because if you put it in spherical, you get a root 1 minus 2 gm by r, and then you can solve the equations, write it down. But if you put the accelerated observer, that is a frame. The acceleration is a frame. Me being in an accelerated observer is me being in a frame. But I can choose whatever coordinates I want. So frames and coordinates are different. Okay. So that distinction will start playing a bit of a role. So I mean, you can do what you're saying, but things will be consistent at the end of the day. Let me do it a certain way, and we'll see that it works. Because psi does not have any index. So if you're just doing GR, if psi does not have an index, what will you do? You'll just do the value. It's not correct. This is of course not correct. So scratch it out. So what is the correct thing is what we should find. Okay. We should make the Lorentz transformation space-time dependent. Then psi will transform as that e to the something something psi, where that something e to the something will have x's. And so then when you take a del mu, things will get more complicated. And then you have to cancel those terms. For that, you have to introduce new fields and so on and so forth. I will show you all of that next time. Since I have 2 minutes, let me say some new things to you. Let me introduce tetrads. Tetrads, they're called tetrads because they were introduced in 4 dimensions. I've been doing spinners in 4 dimensions, so let's remain in 4 dimensions. You can do the whole thing in 3 dimensions, but let's do everything in 4 dimensions. So let's write down a metric in 4 dimensions. Line element looks like this. Okay. Now going to a flat frame, into an inertial frame, is basically writing this as eta. Let me use a bar, b bar. Those are some new indices. Forget about why there are bars and so on. A bar, e a bar, e b bar. Okay. We'll define these for you in a moment. Where EB bar, EA is something that looks like this. The one form. And what I'm doing, so here what do you have? Here you have some functions times the one form times another one form. I want to write that as eta AB times the one form times the one form. This is like going to a flat thing. Okay. So I'll explain this more. I will not use the language of differential forms in the next class. I just wanted to say this quickly since we have 2 minutes. Many of you know differential forms, but I'll do everything in components next time. But let's see an example of this. Let's do Schwarzschild. Let me do the example elsewhere. Note an important fact before I do Schwarzschild. Notice that if E were an exact form, by which I mean if E were of the form this. So E0, E1, E2, E3 are all some df0, df1, df2, df3. Then this just becomes eta AB, dfa, dfb. Okay, so that's pure gauge. So that basically means by a coordinate transformation, you can go to flat spaces. Let's say E were of this form. I'm claiming that given any metric, you can do this. And these E's are what are called cotetrads. Okay. So given any metric, you can do this. I'll show you that for Schwarzschild, for example, you can do this. But now I'm saying for any metric, right? For any curved metric even. But now if E is of this form, then what does that mean? Then ds squared is just eta AB, dfa, dfb. Okay. If E is of this form, this is just flat metric. You can just go to the coordinates where the coordinate surfaces are f, right? You can just go to this coordinates f0, f1, f2, f3. And in these coordinates, things are just flat. So the metric is flat. Okay. So how do you say when a metric is flat given these cotetrads? When the cotetrads are exact, which is when the cotetrads can be written as DFA, the metric is flat. Okay. This is all some fancy language which I will not go into next time. I will definitely not do differential forms next time, which is tomorrow. But I just wanted to give you an example of Schwarzschild. So ds Schwarzschild, ds squared Schwarzschild is just what? 1 minus 2g Newton m over r dt squared plus dr squared over 1 minus 2g Newton m over r plus r squared d theta squared plus r squared sine squared theta d phi squared. if I give you an E0, E1, E2, E3 for Schwarzschild, I should not be able to write it in this form because Schwarzschild is not flat. Okay, let me give you an E0, E1, E2, E3 for E0. I say is just square root. Now this square root is what you got in that acceleration problem. You go to flat space. Next time I'll do everything in these components. But since you know differential forms, you should know that these components actually arrange into a form like this. So here the components are just this comma 0 comma 0 0, 0 comma this comma 0 comma 0, 0 comma 0 comma r comma 0, 0 comma 0 comma 0 comma r sin theta. I'll do everything in those components. But note that this actually is of that form because you do eta ab times this. Eta 0 0 e0 e0 is just minus of that. But minus eta 1 1 times e1 e1 is just dr squared by this, gives you that. Similarly, it gives you that. Also notice that you cannot write this as df, right? Because let's say you write e0 as df0 function of r and t. But then if it's a function of r and t, it will have dt and dr, right? So this is what? This is del x f0 dr plus del t f0 dt. Right? And there is no way that you'll only get a dt if it's both a function of r and t. And it has to be both a function of r and t because this del t f0 has to be a function of r because you have a function of r here. If this were a constant, you could have just pulled it in. It is not. The Schwarzschild is actually not flat. Anyway, so this is what's pure gauge. So this is the gauge theory way of thinking about gravity and so on. Anyway, I think I should stop there. I've taken 5 minutes extra anyway. So next time I will come back. I'll not do all this form business. This form business was just 2-minute quick, nice thingy for people who know and don't get discouraged by it. So next time I will start at the Dirac action and show you how to couple it to gravity, for which I will introduce tetrads and cotetrads. So thank you. Not useful. It's not useful.
Then, I mean, can I say that in sort of that direction, the metric is flat? Say some statement.
I wouldn't say that because then that will become coordinate dependent. When you ask for something to be flat, you need full metric to be of a certain form. Now, you can of course think of like product manifolds, say R2 cross S1, or R2 cross Schwarzschild, where the metric will just be blocks. That's a more trivial example. That's not exactly what you're saying. But it's just flat everywhere. Because that's what flat means, right? Flat means you should be able to write ds squared as eta ab dxa dxb. Yeah, and I found you an f such that it's always flat. It's completely flat. This tetrads, this cotetrads, why we do cotetrads is because you can make it locally flat. Because locally I've written it as eta ab. But anyway, so so doing this in differential form is actually very useful because you have to think of this EA as the gauge fields for diffeomorphisms, gauge fields for coordinate transformations along x, along y, along z, and along t. Okay, and then you have more gauge fields. You have 6 other gauge fields for the Lorentz transformations, and then you have a total of 10 gauge fields. And then you do the same thing as you do in electromagnetism, where instead of A you write dA, and then Once you have dA, you have F, which is F, and then you write F with star F. Do the same business for gravity, you will get Einstein-Hilbert. Okay, but of course, I can't go into all of that. I will do something else tomorrow. Anyway, thanks.